Hello. So as I mentioned in the introductory video, the course will begin with a unit in studying the main algebraic tools necessary for Calculus 3. So primarily we have to focus on the tools required for representing objects or quantities in space. So up until this point in the previous calculus courses you took in the sequence, the main geometric ingredient, if you want, was the so-called two-dimensional coordinate system when you have two axes, x and y. Obviously everybody is familiar with this, in which every point is represented by two coordinates, an x coordinate and a y coordinate. So this is so let's say this is x naught, y naught, just to make a little bit of a distinction between the notation of the axes. And occasionally we also encounter, of course, the three-dimensional coordinate system. By the way, some other notation you may see throughout this course is R2. So R2 denoting the two-dimensional space, or the planar, if you want, coordinate system, right, with two coordinates, x and y. And occasionally you have encountered, okay, in some instances, the three-dimensional system in which each point in space is represented by three coordinates. Let's say a point B of coordinates x naught, y naught, z naught. So this class will require a bit of sketching occasionally, not too much. My philosophy is to basically require just enough sketching on the paper so that you can figure out the meaning of the problem. For anything fancier that might be needed, we're going to use technology. But like I said, we have to also get some drawing skills throughout this class, for quick representations of the problem at hand. So the first two coordinates, x naught and y naught, are just like before, right, in the xy plane, which is seen horizontally in this perspective. And of course, there is a third coordinate which represents the z-axis, the coordinate on the z-axis. So I'll talk about in the more details how you actually label these axes with x and y and z, because it's actually not arbitrary, and it's quite important for the rest of the course. But just to anticipate a little bit of what comes up, the most important the algebraic element related to the three-dimensional space will be the so-called vector. We'll get to that in the second lesson of this class. If you want, really the vector is basically the quantity, the fundamental mathematical quantity, which is at the root of pretty much all important formulas related to calculus 3. When we get to the integrals and some other elements of the course. Okay, so I mentioned already about labeling the axis. So this leads us to the so-called right-hand rule. Some of you watching this or taking this class might know already what this is all about, and some people might find this kind of silly, this convention, but it's actually a very important convention. And in the beginning, until you actually learn enough tools that deal with this convention, you might not actually appreciate why it's there in the first place. Although knowingly or unknowingly, you actually use this convention even before you encounter this concept in a mathematics course. So what do I mean by that? Let me give you a little bit of a motivation why we need something called the right hand rule, which I'm going to refer it later on like that, whenever I'm going to have to quote it. So there are many actually reasons for this convention, but roughly speaking, the idea is that, let's say you have some sort of quantity or formula in which you have to decide whether you actually have to point on one side of a plane. So suppose this is actually a plane, right? And you want that quantity that you want to build or to represent, which let's say it's given by an arrow. We'll get to that later. I mean, you can think of it as a vector. But let's say there is no obvious default way of choosing one side of the plane. There are other reasons for this convention, but let's say the quantity basically gives you that one side of the plane or the other, and you have to choose between the two. And there is no default or obvious way to choose that. That's the whole idea. It is kind of analogous with choosing the positive direction on the x-axis, right? So if I have, for example, the horizontal axis, which represents real numbers, there is no, unless I define it beforehand, there is no default way in choosing the positive, let's say, elements on one side. Let's say this is the origin of the axis. Shall I choose the positive numbers to the right of the origin or to the left of the origin? Now, everybody knows we choose the positive numbers to be represented on the right of the origin from our perspectives, and of course the negative ones on the left. But what I want to emphasize, and this is the key point here, this is just a convention. There's nothing special about choosing this direction one way or another. So there is a convention that positives numbers are to the right. Now, this seems natural for us because we use this so often, it feels automatic that the positives are to the right. But again, the same idea works here with the choosing one side of a plane or the other. Which, if I have to choose one of the two, which one is the default, let's say, positive orientation, which one is the default negative orientation. So we'll get to that on the second page, but the idea is that the right-hand side rule simply defines a positive orientation for one side of a plane. So before we move on to the second page, and by the way, I'm insisting a little bit with the right hand rule, and I know that most people actually know what this is all about, but just bear with me for a moment, because first of all, if you didn't use it before, it seems a little bit confusing, and I think it's also easy to use it incorrectly. I'll get to that in a moment. So for example, if I look at the coordinates, right, x, y, and I have to label the z coordinate, I mean the z axis. Now, shall I choose the positive z values on the top of above xy plane from our perspective, or below it, right? So now again, most people will think that why do we actually have to bother with so much discussion here? I mean, everybody knows that we choose the positive z values on the top of the xy plane, right? So in other words, the positive orientation is above the xy plane, the negative orientation is below the xy plane. So that's where we put the z values, the negative z values. The problem is you have to think now in 3 dimensions. So these planes that may require this type of choice may be skewed, may be inclined, tilted, in other words, from our perspective. So for example, what if, for some relevant quantity, the xy plane is kind of tilted to the left a little bit. And of course, the sky's the limit because it's 3-dimensional, right? You can have this rotation however you want it, right? So in other words, if I have it like that, then what is the positive orientation? Is it kind of to the left or to the right, right? I mean, so that's the whole question here that we have to answer. So there is no default up and down. Again, if you imagine a very general picture when you have this plane. So which way you go if you have to choose one of the two? Well, which way you go if you want to choose one of them to be the positive orientation. Okay, so with that in mind, let's move on to the let's see, I have to actually stop this because it doesn't update immediately for the next page. We'll get to the next page in a moment. All right, so take a moment to write this down. By the way, as I think I mentioned a couple of times during my videos, you should always pause the video to catch up. Because you have this option, sometimes I write in advance some stuff so that I can save time with the video. So the right hand side rule in drawing in labeling the coordinate system, the X, Y, Z, the three-dimensional coordinate system. So this is just for labeling the 3D system. Again, the right hand rule will be used in various contexts, but the concept is really the same. So in other words, if I choose, when you draw the coordinate system, you always choose however you like the X and Y coordinates. This is, by the way, the typical labeling. Well, I'll get you, I'll write a couple of other versions as well. So you get to pick the positive X and the positive Y. Again, there's no special way you go about it. I mean, for example, the way I draw it here, the positive X is kind of toward me, away from the screen. You could also do it in the opposite way. I'll show you in a moment. But you get to choose the labels for X and Y. The question is, what is the positive Z? Is it on the top or on the bottom? Again, it's not going to be arbitrary. It's going to be following the so-called right-hand rule. So how do you apply the rule? Well, obviously you have to use the right hand. That's the key thing. And when I say use it, you really have to visualize it because, and this is where the confusion lies later on for some people. If you actually physically use the right hand, sometimes you'll have to kind of twist your hand to use the rule correctly. So obviously you don't want to do that. You want to actually visualize your right hand doing that alignment so that you can pinpoint the positive orientation. So the first step is to position the wrist of the hand at the origin. So this is going to be your wrist, and I'm going to show you actually a video with me, playing this type of exercise as part of this lesson. So this is going to be your wrist, and then the fingers, except the thumb, okay, all your fingers, align them along the positive x-axis. So this is going to be your, let me see if I can use a different color here. This is going to be your fingers, and this is going to be basically your hand along the y-axis. Okay, so if you want, this is going to be your elbow, right, which goes all the way to the wrist, and then the finger. So you basically make a 90 degrees angle between your hand and the fingers. And once you do this alignment correctly, when you extend the thumb, that's going to point into the, or to the positive Z orientation. All right, so the thumb decides which way you go, up or down, or one side or the other of that plane. Again, by drawing, it's not going to be that easy to see, but I'm going to add a video with me actually showing you how you do this. Now, here's the problem with the right hand rule. Let's say basically I decide to label the coordinate system like that. I decide to do the x axis here and the y axis here. If you use the right hand rule correctly, you'll have to twist your hand a little bit, because if I use the right hand and I want to put the wrist here and I want to align my fingers, as I should according to the rule, along the positive x-axis, I am forced essentially to twist the hand, and so that the fingers are here, the hand is here, and then if you do that, the thumb will obviously point in the downward, from our perspective, downward from that plane. So that's the orientation. Let's say another version. Let's say I decided to, from our perspective, to label the positive x-axis like that and the y-axis like this. Again, you kind of have to twist your hand because, once again, the wrist should be here and the fingers should be along the x-axis. Okay, so then if I do that, then the z-axis, or the positive z-axis, is going to be actually toward the screen, inside the screen like that. To the contrary, if I have x here and y here, then You don't have to twist your hand here. It's kind of easier to visualize, right? I mean, this is going to be your fingers over here. And then the thumb will point away from the plane, or away from the page if you want. Okay, so with that in mind, that's, I think, enough for the positive orientation. Most of the time we're going to use this picture because that's the most convenient one. So basically to have the positive x toward us, positive y in the paper, positive z in the paper upward. That's going to be the most convenient one to use. So I usually spend this kind of unusual amount of time with this, but we're going to refer back to this concept throughout the class, and you will see it's gonna pop up all the time when we have to choose basically one side of the plane or the other. So with that in mind, let's move on to another fundamental concept related to the geometry of the three-dimensional system, namely the distance between 2 points, or the distance formula if you want. Again, some of you might have seen this already before. So given 2 points, let's say A of coordinates x1, y1, z1, and B of coordinates x2, y2, z2, the distance between the 2 points is actually coming from the Pythagorean theorem, and is given by square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Just to be clear, whenever there is no risk of confusion, I may not actually state the formula for both three-dimensional and two-dimensional systems. So for example, if you are in 2D, in two-dimensional system, and you have 2 points, let's say m of coordinates, let's use different letters this time. Let's say m of coordinates AB, n of coordinates XY. Then the distance between m and n is going to be, and by the way, another notation is to actually have this notation, which we can use actually more often, these vertical bars, which you know the distance between the 2 points. That's going to be square root of x minus a squared plus y minus b squared. But notice the formulas are analogous. I mean, the only difference is that for a three-dimensional system, you have another pair of coordinates in that formula. So if the formula is analogous, sometimes I will specify it just for the 3D or for the 2D, depending on the case. But you should always assume that if there is an obvious analogy between the two coordinate system, the 2D and the 3D, then it's going to be it's going to hold in the same manner, so you don't have to spend so much time with stating the obvious. I mean, the same formula all over again. Let's go over a little quick example. So suppose we have a point of coordinates minus 3 to minus 7, and let's say a point B of coordinates 1, 0, 2. So then according to the formula, the distance between A and B is going to be square root of minus 3 minus 1 squared plus 2 minus 0 squared, right? The difference between the y coordinates, and minus 7 minus 2 quantity squared. Let's see what we get here. That's going to be 4. That's 16 plus 4, 9 squared, that's 81. And that's going to be square root of 101. Okay, moving on with a couple of more formulas before we call this introductory, before we finish this up. Just a second. So it's important also to learn some geometric aspects that can be inferred right away from these coordinates of a point in place in space. So for example, let's say I want to figure out the distance between a point A of coordinates -3 to -7 to the plane xy. So the plane made by the xy axis. Let's actually represent the point here. By the way, often if we don't need to actually sketch the point, we can just place it arbitrarily on the paper and just mention the coordinates. If we don't need an accurate picture, we typically don't do that. Like you notice in the previous picture, I didn't actually sketch the 2 points. If I just want to find the distance between the 2 points, you don't need to actually sketch the points in the plane, right? You just apply the formula. But for this little exercise, let's actually do that. So because x is -3, so it's going to be right here. That's going to be the x coordinate. 2 is here. So form a little parallelogram. That's going to be the projection of the point on the xy plane. Coordinate -3 and 2. And then z is further down. Let's say this is -7 here. For another parallelogram, that's the easiest way to sketch the point. So once you label the x and y coordinate, form a parallelogram, that's going to be the projection of the point on the xy plane. So the actual z coordinate, just form another parallelogram with this diagonal, and this is going to be the actual point of coordinates -3 to -7. Again, we're not going to do this type of picture too often. This is just for the beginning. But I did this because notice that the answer to the question was the distance between a point to one of the planes made by the axis. The answer is always absolute value of one coordinate, namely in this case z, right? Because obviously the distance from the point to the xy plane, the distance is given by the amount of the absolute value of z, right? So I mean the distance from the point along the to the xy plane along the z-axis. So that's going to be obviously 7, right? So the absolute value of -7 is 7. So by the same token, and again, you don't need to do this on paper. I mean, you don't have to sketch this. If I ask the distance between A and, let's say, the xz plane, you can pause for a moment and try to answer, but obviously that's going to be the absolute value of the y coordinate. So that's going to be 2. One immediate application of the distance formula, which will be important for later because we're going to use this quite often, this geometric object, is the sphere equation. So if I want to represent a sphere of center ABC and radius R, right? So if you imagine the sphere here, here's the center, and then basically the sphere gives me all the points at a distance r from the center. Well, the equation of anything, remember, it's a description of a generic point on the sphere, right? So if I want the equation of any geometric object, that's another way of saying that I want a general description of a typical point on that object. So because the sphere is defined as all points at a distance r, right, from the center, that's another way of stating that if I take a typical point, let's call it M on the sphere, I want the distance from M to the center to be r. So basically I just restate this with the distance formula, and that gives me square root of x minus a squared plus y minus b squared plus z minus c squared equals r. Now for convenience, we don't keep the square root here. We can square both sides, and this is going to be equivalent to x minus a squared plus y minus b squared plus z minus c squared equals r squared. So for example, if I want, let's say, the equation of the sphere whose radius is 3 and the center is -1, 0, 3. Once again, it's another quick problem for which we don't need any picturing. That's all we have to figure out, right? So then according to the formula, that's going to be x minus -1. You got to pay attention to that double negative, plus y minus 0 squared plus z minus 3 squared equals 3 squared. So if we simplify this, that's going to be x plus 1 squared plus y squared plus z minus 3 squared equals 9. We can leave it like that, or we can manipulate it further as depending on the need for the problem itself. Another fundamental object or geometric figure is a plane. We're going to talk about in more detail how we can represent planes in general, but some typical questions on the homework related to these sections are to again visualize some of these objects just based on what you learned right now, just based on the generics related to the coordinate system and distance formula if necessary. So, and that's I think is going to be the last page. I think I'm going to start a new page. So hold on for a second. So there are some typical questions in the homework in which they say describe in some words the figure given by a bunch of equations or inequalities. All right, so let's start with the basic ones. This is again a very important part of the section, so try not to move too fast over this. So let's say I want to describe, and by the way, the question is in R3, right, in the three-dimensional space. So the first one, let's call it the first problem, right? So I want to describe the picture given by the equation x equals 5. This is again something that people get confused with this part of the lesson in the beginning, and it's important to make sure you understand it very well before you move on. When I state that I describe a picture in R3 by some equations, I'm referring to a description of all the points of coordinates x, y, and z. So the equation provides a restriction, right? Like just like in the previous case with the distance formula or the sphere equation, the equation gives you the condition that the coordinates need to satisfy so that you can generate that picture, a sphere in that case. And here's a remark, a very important remark. In fact, let me actually write it down with a little bit of a different color so that I emphasize it here. If one or more coordinates, if one or more coordinates do not appear in the equation, that means they can have any real value. It doesn't mean that it's zero or it doesn't exist in the picture. If I state that, of course, this is going to be a picture in R3, you have to understand that if there is no specification for y and z in this case, right? So my equation is x equals 5, then automatically it means that y and z have any value, any real value. So they can take any real value. And again, using your imagination, you can realize that this equation x equals 5 in R3, the context matters, we'll get to that in a moment, represents a plane perpendicular to x-axis, perpendicular exactly at x equals 5, right? Why is that? Well, again, let's represent quickly our coordinate system, right? So let's say x equals 5 is here, that's the only restriction. But aside from that, y and z can take any value, right? So all the points in space for which x equals 5, right, as y and z can take any value. Again, the picture is not going to be too easy to represent by hand, but I hope you visualize this correctly, right? So it's going to be a plane perpendicular to the x-axis. once again, the context matters, right? Because what if I say, what is the picture of x equals 5 in R2, right? So previously here, the space in question is R3. What if it's x equals 5 in R2? Well, in this case, there is no z, obviously, right? So the space is going to be given by the xy coordinates. And I think people here are more familiar, right? I mean, if x equals 5, y can take any value, so that gives me a line perpendicular to the x-axis. So that's a very important thing to keep in mind, right? I mean, the context, the space matters. We are in R2 or R3, and then we look at the equation of the picture or the object, and then we decide what it represents. And again, if one of the coordinates, one or more coordinates is not present, that means it can take any value. Here's another example. What if I describe the picture as y greater than 2 in R3? I'm not going to sketch it this time around. Remember, y equals 2. Well, maybe I should sketch it a little bit just to give it some idea. Y equals 2 is right here. If it was y equals 2, it'll be a plane, right, perpendicular to the y-axis, just like before. But this time around, it's not just y equals 2, it's all the y's greater than 2. So x and z are arbitrary. They can take any value. But y also can take any value above 2. So basically what this gives you is this entire region to the right of that plane. We can call this as half space, right? All the points to the right of the plane y equals 2. Finally, another object that you may see occasionally. What if I ask, what is the picture given by x squared plus y squared equals 1 in R3? In R2 will be a circle, by the way. I mean, everybody should recognize this basically as the equation of a circle, the unit circle in R2. But in R3, right, in the three-dimensional space, we have the z coordinate as well. And since this is not specified, remember, that means z can take any value. Well, that means you have basically this circle superimposed, right? So with respect to x and y, you have that circle. If it was just in the plane. And then as z varies, x and y follows the same pattern. But again, z can take any value. What does that give me? That gives me an infinite cylinder. Okay, so if you want just a circle in R3, you will have to say x squared plus y squared equals 1. And if I want the circle just in the xy plane, you're going to have to add that z equals 0. That'll be just a circle. However, if I drop the condition that z equals 0, then that gives me an infinite cylinder, because again, z can take any value, positive or negative in this case. So we're going to go over actually some examples with Maple in the last part of this lecture, before we move on to the most important introductory part, if you want, which is the one that introduces the concept of a vector. So stay tuned for the last part, and then I'll see you next time. Okay, so just a couple of examples and just another quick brief explanation of the right-hand rule. So one, I think I mentioned the word wrist. I think I wanted to say knuckles, right? So I mean, when you actually use the right-hand rule, forget about the thumb for a moment. Like I said, the first step is to align, to make a 90 degrees angles with the fingers and the arm. And your origin of the coordinate system is on the knuckles, seen like that from the perspective. And then the fingers are aligned to the positive x-axis, and the hand from the knuckle all the way to the elbow aligned with the
positive y-axis. So once you make this alignment in your mind, remember, in the beginning, you can play around actually with the hand and do the actual alignment, but later on, visualize the right hand doing this alignment in your mind. Once you do this correctly, let me see like that, right? Then the thumb, when you extend it, is going to point into the direction of the z-axis. So the idea is, roughly speaking, because obviously the biology doesn't work exactly like with mathematical precision, the idea is that the arm, the fingers, and the thumb will basically form the axis of the coordinate, or the three-dimensional coordinate systems. Sometimes people use actually 3 fingers, but that for some reason I don't particularly like that. Although to each his own. I mean, if you find that more useful or easier to do, that's fine. So once again, the whole idea is to use the thumb to decide the positive orientation once you make the alignment between the actual fingers and the arm with the X and the Y axis. So the way we actually sketch the coordinate system in our class most of the time, let me see, it's going to be awkward, more unusual than in the classroom. So the positive Y axis is going to be parallel to the screen, like that. The positive X axis is going to be away from the screen. And that's why when you extend the thumb, that's going to point upward in the positive Z orientation that you're used to. So this kind of configuration, we use it most often in our class. But again, it's important to actually not physically do the alignment, but use your imagination with the right hand, because this right hand rule is applied also in situation in which the plane is tilted or it's switched around, So that means to actually physically align the hand with the X and the Y axis. That kind of implies eventually, twisting the hand. So that's kind of awkward. So before we call it a day, let me go over just a couple of examples with Maple to generate some of the pictures we established just using intuition in the previous part of the of this lesson. Let me share this quickly. So I want remember that important remark I mentioned today, that if one of the coordinates, one or more of the coordinates, is not specified in the equation of that picture, whatever picture you want to represent, then you should assume that that coordinate takes any value. In other words, if you see x squared plus y squared equals 1, that's not just a unit circle, because if I say that this is a 3D object and I didn't say anything about z, that means z can take any value. So that means this unit circle, I mean, x and y still describe a circle, but as z varies, then essentially that circle will generate a cylinder, a so-called infinite cylinder, as you can see it here once we generate this, this picture here. So if you see it from above, from the z-axis, from above, and you only see the variation of x and y, let's see if I can align it like that, then obviously you see a unit circle, right? X and y follow the equation of a unit circle, but as z varies and can take any value, then obviously the whole thing becomes an infinite cylinder. On the other hand, if I fix the value of z to any value you want, let's say here I put 0, but let's say z equals 5, then you're going to have actually an actual circle, but at the level z equals 5, right? So if you look here on the z-axis, z equals 5, and then x squared plus y squared equals 1, so that gives me an actual circle, because now z is fixed. As z varies again, that becomes a cylinder. And then finally here, because I didn't say anything about y and z, x equals 5 is going to be a plane, right? So I mean all the points for which x equals 5, but y and z can take any value. So if I see it superimposed to the y and z plane, then you see essentially all the points taken, y and z, whereas x is just 5, right? So basically this becomes a plane perpendicular to the x-axis at the coordinates x equals 5. So we're going to have other examples like that as we move along with the material, but for now, this is sufficient for our first lesson. So see you next time.